Okay, thank you very much. Thank you all for being here. So let's start with adversarial attacks for machine learning, especially deep learning. And what are those adversarial attacks? If you have worked on deep learning, you have faced this issue of adversarial attacks. Who here works with deep learning? So I can have an idea. And who knows about adversarial attacks? Okay, so I have more people who knows about adversarial attacks than people who work on deep learning. That's how famous adversarial attacks are. So, the idea of adversarial attacks is that you have a model, you make a change on the input of the model, you make a very small change, but it's a purposeful change, it's not a random change, and then the model crashes. It gives a nonsense answer. To give an example, this is an example of an adversarial attack. I have an innocent input, and if I use my model to predict or to label this image, the model succeeds. It will say, okay, this is a very easy image to label, it's a banana. And then I essentially add nothing to the input. As you see, this is the attack. This is the image of the attack. It's very small fluctuations that I added to the image. The result is essentially, to the naked eye, is essentially identical. And then I ask again the model to classify the image, and the model says, okay, this is a mushroom. And not only this is a mushroom, but I'm very, very convinced that this is a mushroom. This is a mushroom with 99% probability. And when this phenomenon was first discovered and described in 2014, people were taken aback, and this was perceived as, okay, there is something wrong maybe with this family of models. This is something that we maybe will be able to correct. And what we have found in the past 4 years is that this is a very general phenomenon. So lots of models suffer from this. And not only deep learning models, but other types of machine learning models suffer from this as well. And it's very pervasive, it's very general, and it's essentially, up to this moment, impossible to correct. So it's a problem that we have with our models, and we don't know how to solve that. So that's it. The problem that the model thinks that this and this is the same thing. And to give a larger variety of examples, I have different classes from ImageNet. This is the ImageNet challenge. So different classes from ImageNet. This is different attacks. Some of them are more visible, some of them are less visible, but the result is very difficult to differentiate from the naked eye. And in all 5 examples, the model says mushroom, 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 mushroom. And this is the classical attack. The classical attack, you want to add small fluctuations across the image to have to fool the human eye and mislabel. After this was found out, different types of attacks were created. There is a new line of research nowadays, which is to create real-world attacks, so things that you can, like labels, small things that you could capture in a camera, for example. In this case, it is idea to create adversarial stickers. So you could print some labels, and when capturing the image with a camera, you would have the results. For example, if I have this picture that I capture from my cell phone, my classifier would say, okay, correctly, okay, this is a banana. But if I print this adversarial label and paste that in my image and I capture again with my camera, it would say, okay, it's a toaster. And the idea here is, okay, it's not to fool by creating 2 imperceptible examples, but is to fool by changing just a small area of the image. This is another example of a real-world adversarial attacks. So the idea here was to create adversarial graffiti. So this is an example that's particularly interesting because of the self-driving cars. So the case here is about self-driving cars. So the research was what kind of changes, what kind of seemingly innocent changes I could do on traffic signs that would mislead the models to not interpret the sign anymore. So doing this kind of intervention, I can render the sign invisible, for example, or I can make the model misinterpret the traffic sign. There are other real-world adversarial examples that are interesting. For example, this is a 3D adversarial model. So they took a 3D printer and they printed the 3D model, and then capturing images of the model, different images of the model at different poses. Almost all of them are misclassified, and misclassified as a particular class, so it thinks that the turtle is a rifle. So this is interesting, and this has implications because misclassifying the turtle as a rifle is not necessarily a problem, but misclassifying a rifle as a turtle might be a problem. So the idea is that, for example, using this kind of attack, someone could mislead a security system and carry, for example, a handgun or something like that without an automated security system raising any kind of alarm. There are other systems which are very impressive. There is a system that makes an adversarial attack changing a single pixel in the image. So the idea, for example, would be to take again the banana example, and instead of adding a small amount of noise on each pixel, would be to put any noise, any amount of noise I wanted, but on a single pixel. So the attack chooses a particular pixel in the image, and it changes that one pixel, and the attack it doesn't succeed always, but it has a success ratio that is very impressive. Okay, let's talk about that taxonomy of attacks and that terminology I'm talking about. The first thing is that the success rate, what I'm talking about when I say that, for example, changing a pixel has a good success rate, but not as good as changing the image everywhere. So this is something that we should know when we want to study adversarial attacks. To attack a particular image, what I do is that I pick that image, I create the attack, so I change that image in order to fool the model. And I will try to fool the model. I will pick one image, I will change it, I will add some amount of noise, preferably a small amount of noise, and I will see if the model is misled or not. And I will measure how many images I succeed or not. And there is this ratio, is how many images I succeed over all images I tried. Other terminology interesting, black box, white box, and gray box attacks. In black box attacks, I must know exactly which model I am attacking. For example, I am attacking AlexNet with those weights trained on exactly that way. I need to have the trained model to make my optimization to create the attack. What is very impressive is the white box attack, in which I don't have to know anything about the target model. I make very general assumptions about the target model, and I do my attack. And there is the intermediate gray box attacks, in which, for example, I may know the nature of the model. For example, I know that it's VGG16, but I don't have the exact weights, or I don't know in which data it was trained. Another thing that is interesting is how universal my attack is. The first way is my attack image specific, or is it, or can I add this attack to all images? This is very impressive. Some attacks are the same for several images. So I don't have to make the attack for each and every image. I create one type of attack, for example, the toaster sticker, and it will work for any kind of image. So attacks that work for any kind of input image are called universal attacks. Another way in which the attack can be more general is that some attacks are model-specific. They will work just for a given machine learning model, and other attacks are transferable. I can do the attack on a particular model, and it will work for other models. So those are the two ways in which the attacks can be more specific or more general. Let's take a little look on how the attack is done technically. I have to switch here to the other presentation. Okay. So let's look at, I want to show you those technical details and all those ugly equations. This is not just to be technical for technicality's sake, but I think it's important to go a little bit on the math of the thing, to understand what an adversarial attack is and what it isn't, and to understand that it's not magical. So there is nothing magical happening here. So let's understand what they do. So those are generalities. So we understand that one layer of our neural network is this linear model. So I have this linear model with my nonlinear activation. This is one layer of my neural network. In general, a neural network will be several layers of that. So you'll have several layers of that. That will have that will compose my network. If I'm talking about deep networks, I will have potentially dozens or hundreds of those layers, and I will train this kind of network by establishing a loss function, and I'll train this using some gradient descent procedure, taking the derivative of this loss function. So this is just to remember the generalities of neural networks. Okay, so the idea of deep learning is that I won't have 2 layers, but I'll have n layers, normally dozens or hundreds. Okay. The idea of doing the adversary attack, when I do the adversary attack, what I'll try to do is, once the network is already trained, so this is the first very important point, I do the adversarial attack on trained models. So when I start the attack, I won't change the weights anymore. So I assume that the weights are fixed. That's the first point. And then what I do is that I will optimize the input. I will optimize the input to change the output. So the training procedure is an optimization procedure in which I change the weights to minimize the loss. This is the training. The adversarial attacks is another optimization procedure in which the training is over. I'm not changing the weights anymore. And now I'm optimizing the input to change another loss. It's not this loss anymore. I'm changing another loss, which is my adversarial loss, in which this adversarial loss wants to mislead the model. Let's take a look at that. This is typically an optimization problem for adversarial attacks. So this is my network. This F is my entire network. If my network, I put some input on it, and I get I get my results. For example, if this is a classification network, the result is a vector of probabilities. Is a vector of probabilities for each of the classes I have. So what I do here is that I will add my adversarial attack. And what I try to do is that I will try to minimize some norm over the attack, because I want the attack to be as little as possible. I want it to be as imperceptible as possible. But I want to have an attack that is enough. It must be small, but it must be enough in order to change the most probable class. So I must change the output probabilities in order for the right class that is represented here by PC, it must not, in the output of the adversarial attack, it must not be the right class anymore. So this is an example on how I can formalize, for example, the optimization involved in the adversarial attack. And now the optimization problem that I'm solving is this one. This is a hard optimization problem to solve. So I can decide, for example, to solve an easier one. This is an easier one. Instead of optimizing this one, I will minimize this one, in which I have an adversarial output that I'm trying to achieve. And I want my output to be close to the adversarial output that I want to achieve in some criteria, for example, entropy or cross entropy, something like that. And I want again to have a small norm for the input noise using some norm. Here I'm using the Euclidean norm. Most often, we will put some restriction on what kind of interval the attack can do. For example, if my images are restricted between 0 and 1, or between 0 and 255, I want to preserve these bounds. I consider that I cannot give a negative pixel or a pixel that is over the interval, because that would make easier for the attack to work. For example, if this problem, if I use this kind of model for the attack, I will use some kind of constrained optimization to solve the problem. So this kind of formulation is very often used to create targeted adversarial attacks, in which what I want is to reach a particular class, or to make, for example, I want my target image to be misled as mushroom. I have a target class that I want to achieve. Another much cheaper way to create adversarial images is the fast gradient sign method, in which what I do is that I take the gradient of the output of the network in function of the input. So what I'm doing here is that I'm analyzing the derivative of the solution in function of the input. And the gradient will give me what is the direction of the major change. So it's the direction of the major fragility of the network. And then I just go in that direction. I take this gradient and I multiply this by some constant, and that's the attack. That's it. This one is not targeted because each image will go to a particular direction. I don't know where this will go. I just know that this is going very far away from where I am, but I don't know in which direction. I move towards this direction, and I know that I'm moving away from the current solution. The advantage of this method is that it's really, really, really cheap, The other method is a constraint optimization. It's iterative. I must do several steps. There are convergence issues, etc. Here it's just to take a gradient and multiply by a constant. So this is really fast. Okay. On the remainder of the presentation, let me take care with the time so I don't go in too much detail. Do you want to present this? No, I'll skip this. Let's go directly to the other one. So far, I've been talking about attacking classifiers because the classical attacks the classical adversarial attacks on machine learning models are on classifiers. But recently, people are trying to attack other types of models. And one model that is very fun, to attack, are autoencoders. The idea of autoencoders, and I think I have a better figure here. Let me show you the motivation. Here, a very good motivation. So the idea of autoencoders is that I have a model, a machine learning model, that takes the input, encodes the input into some kind of reduced representation, and then reconstructs an approximation of that input, an approximation that is as faithful as possible. So I train those models to create reconstructions, to compress images and to recompress input and to reconstruct the input. And recently, one possible application, this has several applications, several types of applications. But one possible application that has been advanced for those kinds of models is data compression. This is not used for data compression yet, but this has the potential for application-specific images, for example, to have much better compression rates than JPEG and other types of algorithms that are not learned. The interest in studying attacks on this kind of model is this kind of scenario. So I can, for example, convince someone to agree on a certain document, and the person looks at the document and say, okay, it's okay, I agree to sign this and to send this to the bank. But when the document arrives at the bank, it's a very different document that arrives at the bank. So this kind of attack can be potentially very, very serious. And this has motivated the idea of attacking not only classifiers, but attacking autoencoders. And the idea here is to make as little as possible changes in the input that make the decoder to reconstruct a completely different model. What we have found, this is a recent article that we have proposed. This is on arXiv. But what we have found is that attacking autoencoders is much harder, fortunately. Attacking autoencoders is much harder than attacking classifiers. In classifiers, it's possible to build examples in which the attack is essentially invisible. The attack is essentially invisible. And the model outputs the wrong class with high confidence. This does not seem to be the case for autoencoders. For autoencoders, you have either to make a harsher attacks which are no longer invisible, either you don't get good reconstructions of the target. Still, you have situations in which if the attack is not invisible, I cannot say that the attack here is invisible. On the other hand, the reconstruction is really catastrophic. You see, what I expected to see here was this. This is the original reconstruction. And what I get is something that is completely different from this input. So this pair, those pairs, this and this, this and this, this and this, this and this, show that it's possible to mislead the autoencoder in reconstruction something that is completely different. So I will finish this presentation by recommending this recent survey there is this recent survey on the subject. This is a fairly recent paper that introduces the terminology that I have told you, and makes a very good work in listing the papers that started the subject of adversarial attacks on classifiers, and then those novel attacks on models which are not classifiers, especially generative models. And it ends the survey by exploring possible defenses on adversarial attacks. The summary, in a nutshell, about defenses against adversarial attacks is that things are possible for classifiers especially. It's possible to do things, but there is no reliable way to defend against adversarial attacks. Especially what we often see in research is that, okay, there is this model that is susceptible to adversarial attacks. Someone creates a defense that is useful. So I create defense D that is useful. And then someone discovers that there is a new attack on the model plus D that renders D completely useless. So the defense is useful as long as the attack doesn't take the defense into consideration. So this is the reality of the state that we are on the defense against adversarial attacks. Because those models, those machine learning models, are becoming more and more important for several security-sensitive tasks, like, for example, surveillance, self-driving cars, et cetera, of course, adversarial attacks is a subject that is more and more studied. So this is a research theme that I don't expect is going away soon. So if you are looking for some juicy research topic that you want to attack, adversarial attacks is a very good one. So thank you very much. And I don't know if you are present for time, if you have time for some questions.
Yeah, I think we have time for some questions, so.
Hi, Eduardo. It's down here. What about subtracting noise? Is it possible, are there any kind of attempts, specifically for the latent parts of the autoencoders, is it possible to subtract noise in a pattern where you also have an adversarial attack?
Let me understand. You want to have a denoising model and then to attack your denoising model, or you want to subtract the model to use it as a defense?
No, the first one.
I'd say that because denoising models have this are often this U-type autoencoder thing, I'd say they will be less susceptible than classification models because they are complex models like autoencoders. So they will be as resistant as autoencoders are, but they will not be completely resistant. I would say that they will be as susceptible, but no more susceptible than autoencoders. That would be my guess.
Hi. So one of the things that I thought was interesting was that this computing an attack, this minimization that you go through, you start with a known point in class A, and you try to find an adjacent point that goes to class B, right? Mm-hmm. So if you took pairs from class A and then class B, and then right before in class A, you have these two pairs, you can build a decision surface on that, and you can build a whole classifier, something as simple as an SVM, that could run without a bazillion matrix multiplications like you have with deep learning. I don't know.
I don't quite get it, but your idea would be because one thing that exists, one thing that is a fact, is that people sometimes feed back adversarial attacks, adversarial examples on deep learning models, and retrain the deep learning models on the adversarial, retrain the deep learning models, and this has a regularization effect.
Okay.
That improves the models. But using the adversarial attacks to create a completely new classifier, for example, an SVM classifier, that is something that I've never heard.
Well, just the idea that you could find the decision surface in the input space.
I
have no idea.
I
thought of it
using adversarial
2 minutes
examples
ago.
to enhance deep learning models. It's a well-known and useful research line. There are several papers on that. But trying to use adversarial examples to create completely new models based on the surface is something that I've never known.
Okay.
One word of warning that I would say is that those surfaces of decision are in extremely high-dimensional spaces. And high-dimensional spaces are really not intuitive. So we have to be careful in trying to think about cubes and spheres and polygons, because high-dimensional spaces, they betray us.
Hi, thanks for the talk. About the optimization problem for the classification algorithm, how can you guarantee the existence of the noise that will trick the algorithm?
I can't always. I really can't always. What often, there are several ways to do the optimization. It's a non-convex optimization because the surface of decision of deep learning is very non-convex. So I don't have any guarantees whatsoever. And people take different approaches. One approach that is very common to do is to limit the maximum norm that I can use, or to use a regularization constant.
Yes, yes.
And then what I do, for example, often is that I do binary search on the norm or the regularization constant, and I try several optimization cycles. And for example, let's see to be equal to 1. Did that work? Okay, no. Then let it equal to be 2, no. 4, no. 8, yes. What about 6? No. What about 7? Yes, okay, let's keep it equal to 7. So I don't have guarantees. I don't have guarantees.
Because I was thinking, if you could find assumptions that would guarantee that it would exist or not, you could discover a way to make immune the algorithm. So it would prevent the existence of the argument to exist. I don't know.
I don't quite follow, but I think in general, if I had a better understanding of how the surface of decision of deep learning works, for example, if I had a better analytical description of how the surface works, I could do lots of things. But one of the theoretical problems that we have currently with those models is that their mathematical behavior is fairly poorly understood. It's not completely, it's not knowledge zero. I know some things, but I have modest understanding on how this math behaves.
Hi, I'm interested in under what conditions of the threat model an attacker can assume that he could work on. Because I assume that for you to be able to effectively solve an optimization problem, you'd need to be able to maybe have access to the weights, which is kind of hard to do if you're, say, pushing an attack against Tesla, a real-world attack against Tesla, or at least be able to effectively iterate your attempts to break the neural network and make it produce nonsensical output. You need at least a way to either fastly iterate over it or have some access to privileged information. So I'm interested in like what constraints could an attacker assume to have in the real-world situation? So
the optimization problem that I showed you is the white box optimization. So I have the model, I have the function, I have the weights, I have everything. This is the white box model, and this is the one where the fooling rate is the highest. I have a great fooling rate with this kind of model. But what people found, and this was very early discovery, is that I can do the white box on a model, and then I can take this example and use it in another completely different model. And then, of course, I will have a smaller fooling rate, but I will not have zero fooling rate. And the fooling rate can be surprisingly high. That has led people to try to make other types of attacks that are black box attacks and gray box attacks. And those can potentially use different optimization targets or loss functions or constraints, which are, of course, more complicated because I have to make less assumptions. What is frightening is how successful those black box attacks can be. They are not as successful as the white box attacks are, but they are frighteningly successful.
Okay, let's thank Professor Eduardo again.